Advanced Math, Lesson 55, Circular Permutations and Distinguishable Permutations. First thing to know about circular permutations, they're very, very different than linear permutations. The reason why is because normally when we do these permutation problems, we think of everything as being in a line, right? And we'll go with the three items being put in a row. All right, let's do it like this. So there's 1, 2, 3, and like this. Ha. Okay, so ta-da. All right, so let's say we've got 3 paper clips and we want to arrange them in a row different ways. If I put them up here, I can go red, yellow, black. That's 1. I can switch these. That's 2. And then I'll go with black in the front. That's 3. And then I can keep black in the front. Do that. That's 4. Then we'll go ahead and put yellow in the front. That's 5. With yellow in the front, we'll switch these 2. 6 different ways that we can put them in a line. Now, if they're in a circle, it changes. Because, let's say, we'll put 3 boxes here. So, the problem with the circle is there is no first square. Because, I mean, if any way I look at this, I could say, hey, the yellow, well, let's say this is the first square, okay? So right now, and then we'll go clockwise, right? Or, yeah, we'll go clockwise. This is the first square. So if I go clockwise, I have yellow, red, black, right? Now let's move everything. All right, it looks different. However, if I start clockwise, I still have the pattern yellow, red, black. Now you may be saying, but they're in different locations of the circle, but permutations don't really care about that. This is the same order, and it doesn't matter if the circle rotates or not. I mean, we could have rotated the circle with them. So if we keep going clockwise, we have yellow, red, black, yellow, red, black. And then even if I move them again, still have yellow, red, black. So the problem with circular permutations is that there really is no first square. So when you do your circular permutations, you can pretty much eliminate the very first square. You can do it without them. So if I was doing this in a linear permutation, I'll do that on top. We'll say L for linear, C for circular. If I were doing these in a linear permutation, I would take the number of options for the first square, which is 3, multiply that by the number of options for the second square, which is 2, and then the last square gets 1. That's going to give me a total of 6 options. Now, since this is a circular permutation, there's 2 ways you can think of this. You can either put 1 in the first square, or you can cross it out and just not use it. I prefer to cross it out and not use it. Our book teaches that you should put the number 1 in the first square. So either way is fine with me. It's easier for me to cross it out because there's no first square that fits logically for me. So whether you use 1 or cross it out, if there is no first square, you then have to look at how many options are there for the second square. In this case, it would only be 2 because the first square is taken, and then the last square would only have 1 option left. So in this case, you'd either just get 2 times 1, which would give you 2 options, or you'd have 1 times 2 times 1, which gives you 2 options. And that's pretty much it. If you're doing circular permutations, however many objects you have, you just have to remember the first square is always 1, or the first square doesn't count. And then because of that, whatever permutation you're doing is always going to start 1 number below the number of objects you have. So that's why we start with 2 instead of starting with 3. And then we'll go ahead and look at the different ways I can shift this. The only way I can really change this up is if I do that, because if I'm going clockwise, I now have yellow, red, yellow, black, or yellow, black, red. And then, you know, if I try to switch these, I'm back to the original permutation, which was yellow, red, black, yellow, red, black. And then I could try to switch these, and then I'm back to the other one, yellow, black, red. And no matter how many ways I try to switch them, I'm only going to end up with 2 options. And then no, going counterclockwise doesn't count as a whole different set of arrangement. So that would be like saying, you know, counting from front to back is different from counting from back to front. Now that's circular permutations. So just remember, when you're doing circular permutations, either don't count the first box or replace the first box with 1, and then do your factorial one number below the number of objects you have. Now let's talk about distinguishable permutations. So distinguishable permutations come from sign problems. So let's say we've got, I'll be completely unoriginal and go with what the book gives us. The book tells us we have the word moo, right? We have these 3 letters, and we want to find out how many ways we can arrange these letters to where we can actually tell the difference, right? Now, the problem is the O's are the same letter. So we could technically have M0102, and then we could have M0201, but do I really know the difference if I switch those 2 O's? I'm not going to be able to tell. These are indistinguishable. So when we're counting these permutations, we only want to go with what is distinguishable. These are indistinguishable. I would not be able to tell the difference between them. So these count as one permutation. Same thing if I were to switch it like this. If I did OMO and then say O1M02 and then I did O2M01. Impossible for me to figure out the difference between those. And then the last one would be OOM, O-O-M, O1, O2, O-M, and then if I did O2, O1, M, I can't tell the difference between those. So in this case, there's actually only 3 different permutations, even though we know that traditionally we would have 3 times 2 times 1, right? Or 3 factorial. Traditionally, we'd have 3 factorial, and that would give us 6. But since these are indistinguishable, we can't have 6. So the solution to this is, if you have repeats of an object, you take the permutation, you take the traditional permutation of 3 factorial, and you divide it by how many times your indistinguishable object is repeated. So the object that I can't tell the difference between is the O. It gets repeated twice, so I'm going to put 3 factorial over 2 factorial, and that will give me my answer. So 3 factorial is 6, 2 factorial is 2, 6 divided by 2 is 3, problem solved. Or another way to do this is I could put 3 times 2 times 1 over 2 times 1, and then I could cancel those. That would be a little bit slower since I'm dealing with low numbers, but if I end up dealing with large numbers like 10 and 5, this is actually very valuable. So now we'll go into a couple of word problems and see if we can spot the difference between distinguishable and circular permutations. Actually, you know what? The book doesn't make you figure that out. They just tell you which one's which. Okay. I'll do one example of this distinguishable permutation then. Let's see here. All right. Hey, I'm going to go with this one because my son's name is Jojo. They tell us Jojo has 10 marbles. Now, of his 10 marbles, they tell us that 3 are red. 3 are blue. And 4 are green. Alright, so there's his 10 marbles. We'll zoom in here so we can see them. So Jojo has 10 marbles, 3 are red, 3 are blue, 3 are green. How many distinguishable permutations can he make out of these 10 marbles? So this is a linear permutation. They didn't say it, but when they're saying distinguishable, they're going to be talking about linear until they state otherwise. So let's look at this. Normally, we would just say 10 factorial, right? But we can't tell the difference between the red marbles or the blue marbles or the green marbles. So I'd take 10 factorial. I'm going to divide it by 3 factorial for the red marbles. Now, that's not the only thing I can't tell the difference between. The blue marbles are also indistinguishable. So 3 factorial for the blue marbles. And then I have 4 green marbles. So 4 factorial for the green marbles. So that's my problem, and all I have to do to solve it is simplify. So, and again, when we're dealing with bigger numbers, the fastest way to do this is to write out the numerator and the denominator in expanded form, and then put the denominator underneath. Here, I'll go ahead and do this in color code so you don't get confused. 4, 3, 2, 1. 3, 2, 1. And 3, 2, 1. The first thing I'm going to notice is 4, 3, 2, 1, all cancel. That's done. Next, I'm going to look at this 6. 6 and 3 cancel. The 6 is now 2. Then the 2 and the 2 cancel. Cool. Another one's gone. Now, in the denominator, all I've got left is 1, 1, 2, and 3. I don't really care much about the 1s. 2 and 3, though, have got to go. 2 can cancel with 8. That will become 4. 3 cancels with 9, and I get 3. In my denominator, I've only got 1s left over, and they don't matter. So, now all I have to do is take 10 times 3 times 4 times 7 and times 5. Might be useful for you to circle what's left so you don't forget about it. And so let's do a quick exercise in multiplication. 3 times 4 is 12, times 7 I get 84. No, hold on. No, that's right. Yeah, 84. Then 5 times 10 gives me 50. 84 times 50. Well, let's see here. I can take 5 times 8. That gives me 40. And then if I add the 0, that's 400. All right, and then 5 times 4, or 50 times 4 is another 200. Wait, no, that should be a 4,000. Yeah, 2 zeros. Okay, so 4,200. That's what I get. You guys can definitely use your calculators, but you know, I just wanted to do it that way. And yep, 4,200 is correct. So that's distinguishable permutations. If you guys have any questions, let me know on Moodle.